Hi, welcome back. In this problem is a homework problem I wanted to do with you because I know a lot of people struggle with this particular problem. It says find the slope of a curve, and I'm going to write the curve here so you can see it. Y equals x cubed minus 9x. At the given point, so there's a given point, 2 comma negative 10, find the slope of the curve at the given point by finding the limiting value of the slope of the secants through point P. And then eventually it wants you to find an equation of a tangent line to the curve. Well, here's the thing. Let's take a look at the curve. I plugged it into the TI here, okay? Let me use Zoom 6. It's your standard window. Okay, so if you think about it logically, 2, let me hit the point 2 here. So here's the point, 2, negative 10. And like I said, if you hit trace and then just hit 2 and hit enter, it should have worked. There we go. There's the point 2, negative 10. And in fact, if I do window, I'm going to change that window there to negative 12, make it a little prettier. The Y min, I'm going to change it to negative 12. So let's see if you can see this, okay? Now hit trace, and again over at 2, negative 10. Sorry for how fussy this is. This virtual calculator is kind of awkward to use. Alright, so there we are at 2, negative 10, and we want to find the slope, basically the slope of the tangent line at that point. Well, the slope of the tangent line, we're at the beginning of calculus, so we haven't talked about how to find a derivative yet. So instead of getting the slope of the tangent line, what are we going to do? We're going to get the slope of the secant line. We know how to do that, the average rate of change through a point, by going, through point P and just picking some, arbitrary point near it. And so instead of getting the slope of the tangent line, we'll get the secant line, the slope of the secant line, as a good estimate. And we know how to do that, good old delta y over delta x. So what I'm getting at is, let me show you a few key features here. Have your table set, have it on ASK. Second table set, it's currently on ASK, which is good. Go to second table. Okay, I'm going to delete all the stuff that's in there. Okay, so at the point 2, just to verify, let me shrink this calculator so I can work with it. It's very awkward right now. Okay, so at the point 2, we see negative 10. Now let's just go, what I'm getting at is go a little bit away from 2. Say 2.01. Hit enter. So at 2.01, the functional value is, negative 9.969, right? So if we wanted to get the slope of the secant line through those 2 points, basically, if we do our delta y over delta x on that, so we'd have negative 9.969 minus 10, which basically means plus 10, over, 2.01 minus 2. Well, let's crunch that out and see what it's going to be. Okay, so negative 9.969 plus 10 is something, and we're going to divide that by the delta x, which was basically 0.01. And what do we get? We get 3.1. But does that mean the slope of the tangent line is 3.1, or is it 3.0? So what we do is we move a little bit closer to 2, because you notice 2.01, that's close, but how about a little bit closer, like 2.001. So what we're doing is we're shrinking that delta x and making it smaller and smaller and smaller. So now I'm going to try, okay, 2.001. And now I see the corresponding y value is this negative 9.997, right? So when I do the delta y over delta x on that, I'm going to have negative 9.997, minus minus 10, which really means plus 10, over 2.001 minus 2. So I'm constantly looking at the slope of the secant lines, and I'm shrinking that delta x by choosing values closer and closer and closer to that key point, values of x. I'm shrinking that delta x to see what happens, and thereby that's the notion of the limit. See how close I can get to the slope of the tangent line at that point. So we're going to take the negative 9.997, let's crunch that out. So negative 9.997, basically plus 10. Oops, let me get out of there because I can quit. Negative 9.997 plus 10 is something. And let's divide that by the delta x, which is now is 0.001. What do we get? Aha, 3. And then if you went out even further, and let me just say that if you went out even further and you choose 2.0001, well, you're just going to get closer and closer to 3. So now, that's why, and I have the answer already there in blue, that's why I was able to say the slope of the curve at the point 2, negative 10 is 3. Let me just draw here. If we go back to the graph, let me sketch on there. You're looking at something like this. So the slope of the tangent line right at that point is 3. And the equation of the tangent line, you might be wondering how I got that. Well, that goes back to good old algebra. Y equals mx plus b. Once you know the slope of the tangent line is 3, then you know y equals 3x plus b, and you have the point that it's passing through 2, negative 10, so you can put that in for x, put that in for y, and crunch out the y-intercept to get the slope of the tangent line. And you see I have the answer as y equals 3x minus 16 as the equation for the tangent line. Let's keep crunching that out, do the algebra. So if I do the substitution, put negative 10 in for y, put 2 in for x, solve for b. Negative 10 equals 6 plus b. Move 6 to the other side, solve for b. Oops, I should say minus 6. So negative 10 minus 6, that's where I'm getting that negative 16 for the b. So again, the equation of the tangent line ends up being y equals 3x minus 16. Okay? And what's neat is we figured on that equation of that tangent line to the curve we didn't use a derivative, we used slopes of secant lines through p to help us figure what that instantaneous rate of change there at that point was going to be. All right, good luck.